that gets rid of your radical. When you square a radical, whatever it is, just comes right out, and this guy gets squared. Now you have cosine squared, get them to one side, solve. Don't leave it like this. Don't leave it like this because you won't recognize it like that. Make sure you change it. Make sure you take the square root of the radical 3 over radical 4 and take the square root of 4. Otherwise, you're not going to recognize it. Now, the problem with radicals, when we did radicals, was sometimes we manipulated our radicals, and when we checked the answers, they didn't work. Remember radicals and absolute values? When we isolated them and we worked with them, sometimes they didn't work. So you're going to have to go, the same rules always apply to radicals. Because you force this to become positive, sometimes it's not going to work. So you need to check your answers. You need to check. Just plug them into your original equation, and check. Okay, in this case, it looks like the negatives didn't work.
Why?
Why?
Yeah.
Because sometimes when you work with a radical, because you force it on the other side and you force everything to become positive, when you plug things in, remember it doesn't work. The same with an absolute value. So the same thing's going to happen here. So this cosine is going to be negative. So if this cosine is going to be a negative, for instance, and then you're subtracting something, could you ever get a 0? Just kind of like this, watch. 5 pi over 6 is over here, quadrant 2. Cosine is negative. So whatever it happens to be, negative something. Whatever comes out of this, even if it's not working in there, that'll work because you're squaring it. This will become negative. So a negative minus a negative, can that ever be 0? No. So sometimes you can spot it without having to plug the whole thing in. Sometimes just go throw it in your calculator. Put your calculator in radians and just plug it back in and check it.
How would you do cosine squared? Because it doesn't...
You would do it the same way. Just say the cosine of 30 squared, but make sure you put the parentheses back there. And it'll do that. Cosine, I'll just put this in degrees for a minute. So if you say the cosine of 30 squared, it should square your cosine.
Oh, okay.
Okay, so that's radical 3 over 2. So that becomes 3 over 4, 7.75. Just put it out. Make sure you close that, otherwise it'll square your angle.
All right.
Okay. Everybody okay with that? Same rules of radicals always apply. Isolate them, square them, and always go back and check them. Radicals and absolute values have those issues. Again, isolate your radical, square both sides, gather your tangents together, take the square root of both sides, don't forget it's plus and minus. And again, you're in the same situation. Where tangent becomes negative, just kind of go like this. If you do something and subtract something, are you ever going to get to 0? No. So those two negatives, where tangent's negative here and here, are not going to work. Sometimes, yes, they do work, so you need to check them. God bless. And if you're going to give me all solutions, again, you can do the 2n pi's, but since they're across from each other, just hook it up and do plus n pi's, where n is any integer. All solutions.
Wait, so is it just x pi or pi over 6?
Yeah, because they're across from each other. Pi over 6, 7 pi over 6.
Oh, so you do have the 7 pi over 6, right?
Well, originally we found 2. So if you do plus 2n pi, you just keep coming around like this and coming this way. It's not, just go 180 this way. This is better to put it in. When they're 180 degrees apart, just do plus n pi. Like originally you look at, well, 4. And you would have done this one plus n pi, you would have done this one plus n pi. This one and this one are not going to work.
Yeah, I just find that.
Yeah.
I forgot about that.
Yeah. Stop me if you have any questions. Why did I reject it? We check it. And like I briefly checked it this way. If the tangent in quadrant 2 is negative, right? No matter what it is, it just happens to be a 30-degree angle, but I don't really care what it is. If I put a negative out here, whatever my tangent is negative, whatever comes out of here doesn't have to come out positive. If in fact that it does, it has to come out positive, right? So a negative minus this can never come out to be 0. Just a quick check. But easiest way, just go throw it in your calculator. Put tan x, just leave it in radians, minus square root of 1 minus 2, and we just squared it. Put your radian measure, parentheses, then square. And then it'll tell you if it's 0, and it won't be 0. But this is a quick eyeball check. Yeah, question?
Why did you reduce it to n pi?
Because they're opposite of each other. You have two that are 180 degrees apart. So just do the n pi, where n is any integer. Okay. Okay, so we factored this. Now remember, this is a half angle. So solve it as if it was a regular angle. Then deal with the half angle at the end. So factor it. Don't worry about the half right now. And if you need to say x squared, plus 2x plus 1. Factor this first. Then throw in your cotangent 1/2 x. You only have one of these. So you only have to solve this once. Just solve it once. Once you get the 1/2 x out there, once solve it for a regular angle. Where is cotangent negative? Cotangent's negative in 2 and 4. What reference angle is this? 45, right? So this is 3 pi over 4. And since it's 180 degrees apart, plus n pi. Now, get rid of the 1/2. Bring back the 1/2. Get rid of a fraction, just multiply everybody by 2. You've got an equation. You have this term, and this term. So whether you divide or you multiply, they all have to get multiplied or divided. Were you good with this, Jordan? Because that was pretty new in the double angles. You got those? That's good that you did. We do them a little differently than with the formulas. So if we expected 2 angles in 0 to 2 pi, and we took half of that, we would get 1 angle in 0 to 2 pi. Since we had to find all solutions in from 0 to 4 pi, then we double that part, then we get 2 angles. Good? Any of the multiple angles, solve them as if they're a regular angle, and then deal with this multiplicity at the end. But solve them first the regular way. If you need to put a different variable in there, and then bring back the 2x, the 3x, the 1/2 x, that's fine too. Okay, now, remember, if you can't factor, what would you use when you can't factor? Quadratic equation. So if you can't factor this, you're going to take the a, b, and c out and throw it into the quadratic equation. A little bit more time consuming, but it happens. So we factor this one. It factors nicely. Now, we can never have an angle whose sine is 2. The range of the sine goes from -1 to +1. So you're never going to reach an angle whose sine is 2. So reject that part. So you only have one angle, which is at 3 pi over 2, and you had to go to 4 pi. Make life easy. 1 pi over 2, 2 pi over 2, 3 pi over 2. That's the angle you want. 4 pi, 5 pi, 6 pi, 7 pi over 2. Just count it around in a circle. You only need to go find one more. Just make it a pattern. If you want to add 2n pi, absolutely. It's probably just easier to just count. Good? that the last one or one more?
There's
Yeah,
two more.
Two more. Okay. Okay. This one's a big one. You've got sines and cosines. First of all, get everybody, or you could do it first, replace it, and then get everybody to one side, whichever way you like to do it. Get the sine out of there. The only one you can take out is the sine squared. Cosine is the lowest it could go. So you have one identity that you must remember. This is your Pythagorean identity. This comes from your unit circle and says x squared plus y squared equals 1. This is why they call it a Pythagorean identity. We replace this x with the cosine squared. We replace the y with the sine squared. And there's your Pythagorean identity. From that, you can pretty much do the other two. So get that out of here. Distribute, collect everything to one side, and then factor. This was not bad because you only had two factors, one set of factors for each one. And both of your signs were negative. So you just had to place the second one maximum 2 times, and you'd get it. We reject the cosine of 3. We don't have one. We look at the cosine of 1/2. And we know that's a 60-degree angle. Again, since you're only going from 0 to 4 pi, if your denominator is 3 pi, it's 3 pi over 3. So this is 1 pi over 3. Then this is 5 pi. Then make this 9 and make this 12. So then you can be one more than 6, which is 7, 1 less than 12, which is 11. Rather than add 2n pi. Or add 2n pi. And these are very, very checkable. Check them in your calculator. They're equations. So equations have to work. Awfully quiet. Are we good with these?
Yeah.
Good. Okay, then your last one. Okay, remember this is a half angle. So
Excuse me, because it was two different reference angles.
when you come down here,
Yeah.
yeah. And that's fine. Oh, this one? Yeah. This one was a little odd. You came down here. Was this side okay?
Yeah.
This side was a little different. This side, you could have left it in degrees if you wanted to, since even though we were doing radians, I would understand it if you left it in degrees because it doesn't come out nicely. However, if we estimate this to be approximately 18, this converts nicely to a radian. Normally we don't have this situation, but this one was kind of nice to, you'd have to use your calculator, obviously, find the angle.
There won't be one like this on the test, okay?
There could be. I mean, you have use of your calculator.
Are you going to use a calculator?
You're going to use your calculator. They're equations. You should be able to check them as well.
Well, how would you get to 18 degrees?
So if I know that, okay, let's say tangent of x is 1/3. I'm just putting the x in there instead of the 1/2. So you do second tan. Give me an angle whose tangent is 1/3. It will be approximately 18 degrees. If you leave your calculator in radians, it's going to give you a decimal. You'll never get back to a pi. Rohan?
Can you do it round it? Because I got like 128 pi over 625 or something. So it didn't work out nicely for me.
No, it didn't work out. Nice for you.
You round the decimal.
I rounded it. How did you leave yours? With the decimal?
18.3.
0.3. Yeah. I would just have rounded this one off. And like if you didn't get this side or if you even left it in degrees, that would be fine. But so now that we see, we'll round it off and try to get the closest to a radian that we can. That's the problem with converting fractions that don't work out nicely into radians. They just don't, that's when we usually use the decimals, not the pi. But since we work with the pi, we leave it like that. We don't get too involved in that. Doing this. So we say, find me an angle whose tangent is, so second tan, 1/3. It's about 18 degrees. Yep. So set it up in radians. That's pretty close. Well, by using 18 degrees also, it allows you to get to a better radian measure, since we just estimated.
John has a question.
When you do that in the calculator, do you have it in degrees or radians?
I just put it in degrees. If you put it in radians, the problem with radians is you get some weird decimal. Like that really doesn't translate to anything. So, because the calculator converts pi to 3.14. So you'll never get back to pi. It'll never be a normal looking thing. Even if you say the tangent of 45 even if I say second tan 1 and I leave it in radians, it's going to come out pi divided by 4. It's a decimal. Your calculator will never give you back pi. It's harder to go backwards. Very first one that we did, well, the first one that we did in class together.
You're recording.